So hypothesis testing is two types. So there is tests of association and tests of differences. So we are going to start with chi-square, which is a test of association. So whenever we are doing hypothesis testing, we are using a sample to draw inferences about the population. From the sample, we draw inferences about the population to which the sample belongs. So now we are going to use the chi-square test for this cross tabulation, saying that from this sample, can we say something about the population, that in the population there is a strong association, significant association between males or between gender and internet usage in hours per week, such that one gender is significantly using higher rate than the other. Can we statistically say that about the population? Because with sample, you might have chosen a sample that is, convenient to you. If it was not selected random, and it is too small of a sample, 30. So only once you make inferences about the population, then you could move, aiming that you will target it for males because they have significantly more internet usage in hours per week. So we move to the chi-square test, which is the first test of association between the categorical variables to see whether there is an association or not. So anyways, so coming to the chi-square test, so the null hypothesis and alternate hypothesis. Null hypothesis in chi-square case is that there is no association. Alternate hypothesis, there is association, and we will test this now using the chi-square method. Now chi-square, we look at the critical value, and this is the 5% zone, and what it means we will see in a while once we do the chi-square test. So let's say in this case there are, we have male, female, gender, male, female, and IUPW, high, low. We had 10, 5, 5, 10. Is it something like that? Right? Now, this is a sample, this is in the sample. Let's say what is the null hypothesis? That there is no association. If there is no association, the frequency there would have been equal. So, which means total is 15, 15, 15, 15. $225. Sorry, here total is here total both sides is 30. So if we calculate the when there is I think we multiply. So in the null hypothesis, we say that there is no association. When there is no association, the frequency in all the four should be equal, which means I think it is calculated by you multiply for the particular cell, you multiply the column total by the row total and divide by the total number of respondents. So which means 15 into 15 divided by 30 will be how much? 7.5? 225 divided by 30? 7.5. So this should be the frequency. Actually, if you calculate, this will be the frequency in all the four cells. This says if there is no association. If the null hypothesis is true, then the case should be 7.5 should be frequency in each cell, right? You multiply for that, but if you want to calculate the So null hypothesis in this case is there is no association. Alternate is there is association. No association means the frequencies in each cell is same. So if we look at the null hypothesis, there is no association. In case of, so in hypothesis testing, we start with the assumption that, assuming that null hypothesis is true. If we assume that null hypothesis is true, there is no association. What would have been the frequency in each 4 cells? 7.5, 7.5, 7.75, right? That is the expected frequency if there is no association. If null hypothesis would have been true, what is the frequency? What should have been the frequency? That is called expected frequency. 7.5 in each cell. And there is something called observed, we got from the sample, which is 10, 5, 5, 10. So if the null hypothesis is true, which means there is no association, the difference between the observed and expected should be less than the critical value. There is some critical value. We will come to that. What is that? So what we do is we calculate chi-square with summation of observed minus expected square divided by expected, and we will get some chi-square value. If we do observed minus expected for each cell divided by expected, here you are getting something called 3.33. And then we look at the chi-square chart for alpha level 95% and degrees of freedom. How we calculate degrees of freedom? Row minus number of categories in the row minus 1, 2 minus 1 into 2 minus 1, both sides is equal to 1. So what is happening here is, we have a sample and we are calculating a chi-square value and looking at some critical value and trying to infer for the population that in the population there is some association or not. As I told, in the hypothesis testing, we assume that null hypothesis is true. If the null hypothesis would have been true, the difference between observed and expected would have been 0. Now we are calculating how much is the difference. And if the difference is so huge, what is that huge? Critical value. If it is larger than that, then we say that it is not, because if the difference is larger than the critical value, then we reject the null hypothesis. So the idea is, we say that if really in the population there is no difference, there is a huge chance that you would have picked up the sample where the chi-square value would have been less than the critical value. This critical value is chosen, this is the 5% and this is the 95%, which means we are saying that if in the population there is no difference between there is no association, then there is a huge chance that you would have picked up a sample whose difference with the expected is not much. But you picked up a sample whose difference was more than critical value. If you pick up such a sample, then which means your initial assumption itself, you are assuming that in the population there is no association, and then when you assume something, you are expected to also draw a sample in which there will be no association. But you drew a sample in which there was huge difference. And if that happens, then you conclude that my initial assumption was wrong, because in this sample there is a huge difference, which means in my assumption H naught, null hypothesis, I should not accept it, reject the null hypothesis. So I will tell you about the this is what is called p-value. We calculate the probability and we look at the chance. What is the chance? We will, so here it is the 5%, critical value is the 5% zone, probability that we would obtain such a sample which has such a large probability to obtain a sample from a population where we assume there is no association. The probability of getting a sample from the, there is a 95% probability that from the sample where there is, from the population there is no association, you will get a sample where there is no association, and there is only 5% chance that you will get. So when you are drawing, if you get a sample which has significant difference with the expected, you conclude that you reject the null hypothesis. We will see, we will take it in a more clear way when we move to the sampling distribution in the t-test. It might become little more clear if there is some confusion here. So do you understand the idea of p-value and critical value? So simple is, we assume that H0 is correct. If H0 is correct, which means in the population there is no association. Now if in that population you draw a sample, it is like if your null hypothesis, your assumption is right, in that sample the observed minus expected difference should have been less, but you are getting a big difference, and that is big difference, such a big difference that you are likely to obtain that difference only in 5% of samples from that population, and you cannot be so unlucky that you pick up that 5%. So as you assume that you are not so unlucky, and there is a significant difference, your assumption is wrong, so you conclude that you reject the null hypothesis. So we will do the chi-square test now, and go to analyze. It's the same, go to the crosstabs and we have to go to the crosstabs. Just we have to now click on the statistics and analyze.
So what's the difference between critical value and p-value?
Critical value is the chi-square critical value, which means the difference, how much should have been the difference. So so critical value, it will give you cutoff. Critical value is the value which you obtain from this formula, and it will be in some units of, or it will be the it is a frequency, so you will get some value that this higher is the difference between the observed minus expected. Now how high is too high that we reject the null hypothesis? That is the critical value, which decides if value is larger than this critical value, then we say that, so higher than the critical value, there is a critical value, higher than the critical value, the probability, p-value is the probability that you will obtain a sample, that you will select a sample that has a difference chi-square value of greater than this critical value. That is the probability, how much probability is there. So alpha, that we say alpha is 0.05, which means 5% probability, which is p is equal to 0.05. So we say greater than, let's say if this critical value is 3.1, so which means what is the probability that you obtain a sample higher than this difference, and this probability here, it is written only 5% probability that you obtain a sample higher than you obtain a sample which has chi-square value higher than 3.1. So we go to analyze, descriptive statistics, crosstabs. There is a video also, I have made a video, I will send you the link for the chi-square. So let's do this first, chi-square analysis. So we have rows. 9th one we are doing, 11th one, do a chi-square test between gender and internet users. Gender is row and column is IUPW column, cells this one, And in addition to this, now we will calculate the test statistics, chi-square statistics, and we will look at the probability value, p value. If the p value, which is the probability value, is less than less than equal to 0.05, which means in the critical zone, then we say that, then we reject the null hypothesis. Otherwise, we will not reject the null hypothesis. Oh, sorry, column. Yeah, sorry. Column should be gender. Yes. So descriptives, cross tabs, reset. Column is gender. IUPW here. Statistics, we will put chi-square and click on. This is fine. Chi-square is fine. In cells, percentages. So in the statistics, you have chi-square and other measure also, like phi coefficient is there, contingency coefficient is there. They are also useful, but we'll stick to this chi-square. They are also chi-square statistics, but little adjusted. So if we click OK, we are getting 0.068. This is two-sided. We have to look at two-sided, this one. Asymptoted significance. This is p probability value is 0.068, which is greater than 0.05. And when we are using 2 cross 2 matrix, it is a special case, so we do not look at the Pearson chi-square, but we look at the continuity correction. For 2 cross 2 and for 2 cross 2, or when the observed frequency in any cell is less than 10, we use the continuity correction. Let's say if this would have been 3 cross 2 and observed frequency in any cell, every cell is greater than 10, then we need not use this continuity correction. We have to look at the two-sided p value. So p value is given 0.068, but we are not going to look at that because this is a special case, 2 cross 2. So we are going to look at 0.144. This value, continuity correction, it is an adjustment to the chi-square value, and this we look at in special case when we are looking at 2 cross 2 matrix, or in any of the cells observed value frequency is less than 10. And we should use chi-square only when the observed in each cell is greater than 5. Otherwise, we should not use it. Now do a chi-square for familiarity and internet usage, which is the last one, 11th one.
So how we can conclude whether this?
So we conclude, so p value, if you look at 0.144, which means it is not greater than the critical value, which is 3.33. 0.144 is the probability value, which is greater than 0.05. It is only when the probability is less than equal to 0.05 we conclude that there is an association. See, it is very simple. So when somebody, let's say in a murder case, when somebody is an accused, okay, in a murder case when somebody is an accused, so court, what does it say? Innocent until proven guilty, right? Innocent until proven guilty. So null hypothesis is innocent. So here also no association, no difference. That is what is null hypothesis. And court says that we assume the person is innocent until you have a strong evidence. Here also what we are saying, we assume there is no association until you have an evidence. So we start with the assumption that we assume null hypothesis is true. Let's look at any evidence contrary to that. That is what we are doing in hypothesis testing. We follow the justice process and say that there is no association, there is no difference. Then we look at any evidence against that assumption.
The continuity correction, it's given through two-sided tests. So, and can you please explain again what exactly it's done, what it does in?
So continuity correction, it is not the mathematical formulation. It is not within the scope of this course, but it corrects the Pearson chi-square, which has little bit of incorrectness in case of 2 cross 2 matrix. Some adjustment is required to improve that, and that is why we look at the continuity correction in the special cases when it is a 2 cross 2 cross tabulation, or when in any of the cell the observed frequency is less than 10. Then we use continuity correction, the p value corresponding to continuity correction, rather than looking at the Pearson chi-square. Yes, we look at two-sided p value here, although because in the chi-square we are looking at only one end, and we are giving total. Generally, when you see, if you are looking at two-sided, so it will be 0.025 one side, 0.025 one side, but in chi-square we look at 0.05 on the, but here the value which we are going to look at is under the column of two-sided, whatever value comes here. Asymptotic significance, we are going to look at the value under the two-sided, but it is the value which is on the farther side of the chi-square, which is a positively skewed one, and it cannot be negative because what we are doing is observed minus expected square. So it is made in such a way that it will have positive values only. Do the next one between familiarity and internet usage. Now familiarity and internet usage both are categorical. Go to analyze. The next one is 12th. Do a chi-square between familiarity and internet usage. So analyze. Cross tabs. Familiarity and internet usage. So familiarity will go where? Column. Row. Go to statistics. Chi-square. Continue. In cells. Percentage is column wise. Continue and click OK. And what are we getting now? So what you are getting 0.01, which is less than 0.05, which means there is a significant association. You reject the null hypothesis, right? And accept the alternate hypothesis. 0.01 you see, continuity correction. 0.01 is less than 0.05, right? So less than equal to 0.05, which means the probability is only 1%, which means our initial assumption of there is no association, null hypothesis itself is wrong. We reject the null hypothesis because the p value here, you look at, it is continuity correction, it is 0.010, less than equal to less than 0.05. If it is less than 0.05, which means the probability is so small for obtaining such a sample, which means if in the original population there is no association and then I obtained this sample, it is only 1% chance. This is what it is saying, that it is 1% chance that I obtain such a sample where this difference is so huge, and I cannot be so unlucky that I get this 1%. So I reject the initial assumption H0, that there is an association. So p value here is less than 0.05. Continuity correction, are you getting 0.01? 0.01 is less than 0.05 or no? Are you sure? 0.01 is less than 0.05, right? So where is the confusion? There is a video I wanted to show.
Good afternoon, student. This is the second video of the series wherein I am discussing the chi-square test. Now, after you have done the data cleaning and the basic descriptives and plotting the graphs, this test comes if there are categorical variables and you want to see whether there is a relationship between categorical variables. Categorical variables are nominal in nature, if you remember that. So here we want to understand whether gender has any relationship with feeling stress in times of COVID. So gender is measured as male, female, and feeling stress as yes or no. And these are respondents of 20 men and women, 20 male and female. And to do the chi-square analysis, we put the variable and their categories on x and y axis. So we can do categorical with two variables at the same point of time. So stress, if you see yes and no, male and gender, male, female, yes and no. So how many males, if you count, how many males have feeling stress in times of COVID? It is 16, yes, and 4 no. And females 18, no. And if you count, females are 18 are saying no, and 2 are saying yes. So 90% and there 10%. So you see the percentages will give you some idea whether there is a relationship between gender and the feeling stress in times of COVID, or whether there is a difference between the male and female in terms of feeling stress in times of COVID. So 80% are feeling stress and 20% are not. 10% are feeling stress for females and 90% are not. Now, by looking at percentages, you see that there is a difference between males and females. Now, is there a way to quantify? Yes, there is a chi-square test. Now, what chi-square does is, chi-square test involves observed, this is the formula, summation of observed minus expected whole square divided by expected. Now, what is, these are observed values, 16, 2, 4, 18. What is expected? Expected is expected is assuming that there is no difference between, there is no relationship or there is no difference. What will be the number in these cells? So expected, when they are assuming that there is no difference, the number will be 10, 10, 10, 10. So expected for this cell, observed is 16, expected is 10. You can calculate that and do it for those all 4 cells and calculate the number. That will be chi-square number. And in chi-square number, whatever you get, you have to see the chi-square table at 95% level of significance. If that value is beyond a critical value, then you say that there is a difference. There is a difference between feeling of stress between males and females. If that particular chi-square value is within the critical value, less than the critical value, then you say there is no difference. So by computing observed minus expected for everything 16, so for first one it will be 16 minus 10 divided by 10 plus then this plus this, you will get a chi-square value. Suppose you get 25 chi-square value, and chi-square is and critical value in the chi-square table is suppose 3 and 25 is well beyond 3, then it means this value is significant. There is a difference between males and females feeling of stress in times of COVID. So this is the chi-square test. Thank you.
So the next one, familiarity and internet usage, you have done. Now before we move on to the next sheet, wherein we are going to begin with the hypothesis testing for differences. So hypothesis testing, as I said, there are 2 types. One is test of association and test of differences. Test of differences where we use t-test, independent sample, t-test and so on, that we use in test of differences. I want to draw your attention to sampling distribution. You know what is a sampling distribution? What is a sampling distribution? So let's say I want to know the average height of BTech students at IIT. How many BTech students are there? let's say 4,000. I want to know the average height of BTech students. I cannot go to 4,000 and not possible. Everybody will not be willing to, right? I'll be kicked so many times. So what I do is I randomly draw sample 30 of size 30, and let's say I calculate the average height of that group is 5 feet and let's say 4 inches. One sample I draw, this is the mean height. Second sample I draw 5.5 inches. Third sample I draw 5.4 inches. Fourth sample 5.6 inches. Fifth sample 5.8 inches. If I keep drawing this sample infinite number of times, I will end up with a curve like this. Which means for each sample of size 30, if I calculate the mean, I will get most of the samples, the mean would be around the population mean, which is called mu. Most of the samples would be here, their mean would be, so this is the frequency. Most of the samples would have this mean, which is the population mean. And then, so let's say this is 5.6, and this is some samples I will get greater than, some sample I will get less than, and this is 95% of the area, let's say. This is called a sampling distribution entirely, which means when I draw a sample size of 30 and take the mean of sample, their height, and I keep doing that 30 sample size from population of 4,000, I keep drawing and draw this frequency curve, I will get a frequency curve like this, wherein in the middle, the highest frequency will be the mean with the highest frequency will be the population mean, whereas on sideways the frequency will be lower and lower, and like this. This becomes the sampling distribution.
You are plotting the.
I am plotting the mean of the sample drawn, and I will get a curve like this with most of the samples of the size 30 with the mean same as the population mean, the actual mean of the population. This is called sampling distribution. And why I am telling you this, because this we use in hypothesis testing of differences quite a bit. So in the sampling distribution, the mean of the, in the sampling distribution we draw the means for a particular characteristics for a particular characteristic in a population, and we try to see that the sample size is 30 or greater than 30. When the sample size is 30 or greater than 30, the sampling distribution will be near normal, whereas when the sample size is less than 30, the sampling distribution will be not normal. And many of our statistical tests have the assumption of the sampling distribution as the normal one. So once we understand the sampling distribution, now we can go a little bit further to see how it is used. Now let's say that I tell in this class, let's say that since I am your instructor, I can tell anything, I can brag about anything, and I assume that there is some level of trust and you might believe that. Let's say I tell you that at my house there is a backyard where the coconut trees are there, and the average height of trees, average height is 100 meters. Let's say I tell 100 meters. And you say, okay, this instructor has been teaching us for long. Till now he has not lied. So let us, some of you would say 100 meters is too much, but it's okay. He is saying let it be, might be true. There is, okay. Now one among you is very smart. He says that I cannot let him do this. I cannot let him lie. So he wants to do hypothesis testing. Now in hypothesis testing, as I said, he assumes that H naught, let's say, because I am going to do hypothesis testing, but since he taught me, I assume that what he says, let me assume that null hypothesis is correct. Let me assume that null hypothesis is that the population mean average height of trees, coconut trees in his backyard is 100 meters. So we do this innocent until proven guilty, trust until proven that he is lying, and H alternate is mu is not equal to 100 meter. So I assume that the average height is 100 meter. Who is that person? Then that person went to my home to test his hypothesis. Who is that person? So he went to do the hypothesis testing. So his assumption, what is his assumption? His assumption is what instructor is saying is true. Assume that what he is saying is true. So which means if we draw sampling distribution, nu will be, assume that this is true. Which means assuming that instructor is true, what is the probability? So now what he does is, once he goes to my home, he randomly selects 35 trees and he measures. He does a training before coming that how to measure the height of the trees, and then he measures for a sample of 35. He measures it and he gets the average height as 9 meter. So 9 meter is here. So he says that instructor was saying that it is 100 meter average height. I assume that this is the population mean, assuming that he is right, assuming that the null hypothesis is correct. What is the probability that in a population where the mean height is 100 meters, I am able to draw a sample with such a less mean height? What is the probability? If the mean height is 100 meter, how unlucky I am how unlikely it is for me to select a sample with such a mean height 9 meter. So if I see it is 1%, which means there is only 1% chance that you select such a sample. It is so unlikely, and you cannot be so unlucky that you get that particular sample, right? So what you do is, if you assume that null hypothesis is correct, which is population mean is 100 meters, null hypothesis is correct, it is very unlikely that any sample would have, mean height of 9 meters. So if it is very unlikely, so what is your assumption? That population mean is 100 meter, which is wrong. So you reject the null hypothesis, and this is what we call, this is 2.5% and this is 2.5%. If the value falls here or here, which means there is only very 2.5% chance of something happening here, 2.5. If it is so unlikely, given that we assume null hypothesis correct, in those cases we reject the null hypothesis. So what we do is, we start with the assumption that okay, instructor has said it is 100 meter, assume that it is correct. Now if it is correct, let me draw a sample and its mean, how likely is that I am to get such a mean 9 meter? It is very unlikely, which means the initial assumption would have been wrong. That is how we do hypothesis testing. Is it something clear now? Right? So this is the sampling distribution I am using to do this is one sample t-test. We will be doing in the next class. yeah, so we will look at here. This will be the way we will be doing one sample t-test, where we will be seeing whether the mean, whether the population mean is equal to some value, which assume, let's say, yeah.
How could it be t-test? The sample size is 35.
Yeah, so what I am saying is, in the next class we will use this to do a t-test. Let's say one sample t-test, wherein we'll say, in a population, let's say we want to see whether the mean is equal to, for familiarity with the internet, we want to see whether the mean is equal to 6 or not. So we will assume that, let's say the mean is equal to 6, mu is equal to 6. What is the probability that from the sample the mean is, let's say, 2.5? If it is less than equal to 0.05, we reject the null hypothesis. If it is, so we can use this particular sampling distribution, this concept, to do one sample t-test, then we will use it to do independent sample t-test. But sampling distribution and p-value understanding is very important to get. I hope to some extent you got it, right? Let's end the class here and we will meet in the next class. Thank you.